presentation. I'm going to talk about particles and vortices, quantum vortices in counterflow turbulence. Basically, this is the topic of my talk. And can you hear me well? Is that okay? Okay. Where's the, okay. So this is just a paper that I sent a few days ago to the archives. So for the ones interested to take a look, I suggest that you go there for the details. Okay. So this is the outline of the talk. I will start to reviewing a very brief review here about how quantum vortices can be detected, how they can be observed. Okay, and then we will jump to some very interesting surprises that you. No, it's not okay. Here? No, sorry for that. Okay. So there are some surprises when you try to apply some standard methods that have been used in the detection particle, using this particle tracking velocimetry technique that is kind of common in classical fluids. But when you try to apply this in superfluid turbulence, then you'll find interesting surprise. And the idea here is to study what's going on with the particles. Sometimes they do strange things. We want to understand that. Okay, so I am going to address through a very simplified model. This is a two-dimensional model. I'm going to explore the analytic power of two-dimensional fluid dynamics. I am going to discuss the possibility that the particles can get attached to vortex rings, quantum vortex rings. Okay, so we can see that, in fact, you can have stable bound states here, and the drag of these particles will be affected by this attachment of the particles in the vortex rings. Okay. Then I will show some simulations of the dynamical system. We have a two-dimensional dynamical system here. We can explore. It's a huge phase space, but then we can get some hints from physical parameters that you have from the three-dimensional real case. Okay, and then I conclude with summarizing the results and mentioning some open problems. Interesting to do next. Okay, so this is as it was commented by the other Luca here before. This was a technique that was introduced a while ago by Bewley and other guys here in Advice. I think Lathrop and Pauletti maybe. It's a paper on Nature. Basically, you can you throw hydrogen, gaseous hydrogen into the superfluid. And then they solidify, okay? Hydrogen gets solidified inside your vessel, okay? These are small particles, then they are pulled by the vortex filaments, the quantized vortex filaments. Okay, we know that the pressure is depleted here around the vortex filament. So these particles, they have the size around 5 micrometers or so. They can get attached to the cores of these vortex filaments, okay? Now, these people have been using deuterium, I think, also. Deuterium is more interesting because it's neutrally buoyant under certain conditions. So they're more interesting as tracers, while hydrogen is, I think, it's heavier or lighter. I don't know, but they depart a little bit from the trajectories imposed by the normal flow. Okay. So this is a screenshot of a video that was produced by Fonda. You can find this in the YouTube. It's a very nice video. That's the video. We can see reconnections of vortices. Okay. Here it goes. I will stop at some moment. Okay, here, so here you have the two. You have the vortex filaments. They are going to collide. Okay, at this point, and then you have all of a sudden. Oops, sorry for that. Okay. Let's go again. Here. So you can see the reconnection going on. Okay. Very nice videos. There are hundreds of these videos you can find nowadays. So here you see a filament. It's a huge thing. This is on the scale of 1 millimeter, I think. And so it's a huge object, topological object. The circulation is quantized around this vortex filament. Okay, and it's a very interesting. So people could see phenomena that was hidden from observation, like Kelvin waves. You can see waves going on these vortex filaments. Very interesting technique to explore. But you see here, you have thousands of particles that are not attached to the vortex filaments. So you would like to follow them, okay, to see what they are doing. In this way, you can get some information about the global properties or even local properties of the flow. See here, typically, you have a counterflow where normal flow is flowing in one direction, and superflow is flowing in the opposite direction. Okay. Once a particle gets trapped in a vortex filament, okay, its fate is determined by the vortex filament. There is no way to escape, because if the vortex filament is displaced just by a little bit, you have a strong pressure gradient field that will pull the particle. So the particle is enslaved by the vortex filament. And the vortex filament follows the superflow just because of Kelvin's theorem, okay, of fluid dynamics. That's basically what happens. But if you have a free guy, a particle here, of course the particle will interact strongly with the vortex tangle. The movement will be affected by the vortex tangle. So if you want to extract things, ideas, phenomenological ideas, if you want to understand what is going on with this flow, you have to introduce some modeling for the interaction between particles and vortex filaments. Okay. Yes? Oh, yeah, there is a couple of Kelvin waves here. I will repeat the video. Just pay attention. Look, they oscillate a little bit. There are videos that are even more like significant, where you can see things going like this. But yeah, right. Well, these are Kelvin waves in the presence of particles trapped in the vortex filament. So I'm not sure if they are, maybe the dispersion relation is changed. I'm not sure about this. But right. Well, it has something to do, but I think this is a different regime. You can have vortex structures like very small. In principle, you have Kelvin waves there, but they are very hard to observe, I think. Yes. Yes, what? Okay. You're tough, Chairman. Yeah. Okay, so one of the very peculiar things that was observed by Van Siever and Zhang in 2005 was that, contrary to what you see in classical fluids, the particles that are dragged by the normal flow, by the classical flow, they tend to follow the classical flow with the same velocity, okay? But in superfluid turbulence, counterflow turbulence, it was noted that the velocity of the particles would approach half of the velocity of the normal flow. They were like, their movement was held by some interaction with the vortex tangle. So this is a paper, soon after these results, experimental results, there was a paper by Sergeyev, Bareng and Kivotidis in 2006, where this is a very appealing picture, where a particle that was trapped in a vortex filament, okay? So we have strands of vortex filaments here on the downstream position. So the superflow here, for instance, is going from left to right. And here at right, you have a depletion of the pressure field. So the particle is pulled back, okay, against the normal flow drag. And this way you can do some estimate computations. This is done in the paper. And then you can find that the velocity goes rescaled by a factor of 1/2. This is the content of this paper. More recently, last year, there was this very detailed paper, experimental paper by Mastracci and Guo in 2018, okay, last year, where they changed the flux, the heat flux. So this is the bottom of your container, and this is the top. You have the bottom is heated, So you have some heat flux that goes from the bottom to the top of the container. And they changed the amount of heat flux to see how the particles would behave. So they found that if the heat flux is really high, okay, basically you have just one peak, one velocity peak, which is the normal velocity of the normal component divided by 2. But if you consider heat flux which are not so large, intermediate between strong and weak heat flux, then you have a mixing of two peaks. One of the peaks is at the normal velocity Vn, and the other peak is at Vn over 2. You start to see two peaks here. And if you go down with the heat flux, okay, if you consider even smaller values for the heat flux, then you have a very sharp peak at the velocity of the normal flow. So here you have these straight lines, red lines. They are just the particles following the normal flow here. You have red distribution associated to the red trajectories here, okay? But you have a bunch of particles, okay, hundreds or thousands of particles that go opposite to, well, they claim in the abstract that this peak would be a peak at Vn over 2, but to me this is a negative peak. It has been published anyway. But to me this is, and this is going to be an important thing here in our discussion. This peak to me is really a peak on the negative side. So these blue trajectories are in fact trajectories which have velocity distribution peaked at negative values. Okay. Okay. So getting back to the paper I mentioned by Sergeyev and others, I think that there is a stability issue here. So maybe I would like to hear from you what you think about that. But this is a particle, okay, and you have here the vortex strands. If you consider a superflow approach in the particle from the left here, okay, of course the superflow will surround the particle in this way, okay, and we know that the no-slip boundary condition doesn't apply here for this problem. So the vortex, by Kelvin's circulation theorem, the vortex will be advected, okay, towards the position here near the stagnation point. So they're going to get so close that eventually, probably, they're going to reconnect and be expelled from the particle. So from the fluid dynamics perspective, this configuration is not stable. Okay, so I think that we should look for configurations which are connections, okay, attachments between particles and vortices which are stable. There's some hint of maybe what is the thing that we should look for in this paper by Kivotides and Wilking, published in the JFM 2008. So they studied the collision between vortex rings and particles, okay, and in some examples it was interesting that you had like vortex rings being produced after the collision. So the collision eventually, or casually to say it better, can produce vortex rings, okay, and can produce also handles like this one. So we have a vortex here colliding with a particle and producing a handle, which by the fluid dynamics argument, again, you expect that this handle will collapse. So these two points here where the handle is attached to the particle, okay, they will approach each other, okay, just because if you have some external superflow approaching the particle, okay, surrounding the particle, and then maybe you can produce vortex rings which have the size, a similar size to the particle. So the idea is that when you have interaction, collisions between the vortex the vortices, the quantum vortices and particles, you can produce vortex rings, and these vortex rings, they can interact and form bound states with the particles. This is the main claim of this talk. Okay, so if here I have a symmetry plane cut with a configuration which has axial symmetry, okay, so this is a vortex ring cut here. It's the vortex filaments leaving the screen here, this red dot here. So you have a positive vorticity going out of the screen, and here you have negative vorticity going in the screen, towards the screen. Okay, it's clear that this vortex ring will propagate to the right. Okay, but it's subject to some contributions, different contributions. One of them is the background superflow, which tries to pushes back the vortex ring, okay? And another one is the vortex ring image. So inside the particle, if you treat the particle as a sphere, you have a vortex ring here inside the particle. And the velocity, the superfluid velocity here, okay, out of the particle is the combination of background, the velocity field produced by the vortex ring, and the vortex ring produced as the image inside the particle. And this way, the vortex, at some point, okay, its movement will be dominated by the vortex ring image when it approaches so close to the particle. It will be advected to these upper regions here, or downwards, okay, if you look at the symmetry on the other side here. But at B, the background superflow is even more intense. Okay, we know that the superfluid velocity is stronger close to the here to the particle. Okay, I think it's almost twice the external asymptotic superflow velocity, and such that the ring down here at the position B can be like thrown away to the left. Okay, but then you have a cycle that will be reestablished. So after some iterations, you can develop like an oscillating vortex ring on the back of the particle. So that's the image. You have a sphere, and you have a vortex ring which is oscillating, okay, in a stable orbit around the particle. Okay, so this figure, this configuration suggests that we go to 2D modeling, where the sphere is replaced by a disk, okay, solid disk, and the vortex ring is replaced by a vortex dipole. This is the topology of the flow is basically the same, but now we know how to compute this exactly. This is a textbook discussion, okay, into dimensional fluid dynamics. So we can take advantage of these of the mathematical structure of two-dimensional flows to see what happens with the dynamics of these vortex structures here. Okay. So this is the toy model we are going to consider. We have a disc-shaped particle which has radius r. Okay, place the position ZP. So this is a complex variable description. The positive vortex here has position Z plus. The negative one has position Z minus. Okay, we are considering axial symmetry in 3D. This means that we have a mirror symmetry here in 2D. So Z plus is the complex conjugate of Z minus. Okay, and ZP is real all the time, just because of symmetry. Okay, use the velocity of the disk, which is just the time derivative of ZP. Okay. So these are the basic elements that we consider. And we have an external background, okay, flow. So normal flow goes from left to right here, and superflow goes from right to left. And we're considering the situation where the densities of normal and superfluid components are the same, so that both velocities have the same absolute value. One is V and the other one is minus V, just to simplify all the discussion. But of course, we can generalize it easily to other different situations. Okay. Of course, this is a toy model, so we have some freedom to postulate things that sound interesting from the phenomenological side. Okay. One of the things is that we want the particles to be dragged by the Stokes law. Okay. We know that it's an open analytical problem. To my knowledge, in 2D, the creeping flow at low Reynolds number is an open problem in 2D. But we can borrow what we know from 3D. Okay. So the drag force will be given by some constant here, drag coefficient, multiplied by the particle radius, multiplied by the external velocity minus the velocity of the particle. So that when the particle's velocity is identical to the external velocity, you have no drag. You reach the asymptotic velocity. Okay, so this is the friction force that acts on the particle due to the normal component of the flow. Okay, another postulate is that we want to bring into the two-dimensional discussion the Schwarz description of vortex evolution. So this is what you get when you just adapt the three-dimensional Schwarz description. You have a Magnus Force. Okay, so the red curve here is the vortex filament. Okay, S is the tangent vector to the vortex filament. VL is the velocity of this point here, the vortex filament. VS is the superfluid velocity, the external superfluid velocity, and Vn is the normal velocity. Okay, so Schwarz he considered the forces that act on this vortex filament, and on the assumption that you don't have, let's say, n mass here. The sum of forces is 0. You have Magnus and the drag forces related to the interaction of the vortex filament with the normal components of the fluid, you get an expression for the velocity of the filament, which depend on some coefficients here, alpha and alpha prime. These are the so-called mutual friction coefficients. They're associated to the Magnus force and the drag force exerted by interaction with the vortex. Yeah. This is a complex variable, so right. The Magnus is orthogonal to, it's like here. Magnus force is orthogonal to the tangent vector. All right. So when you go to 2D, you get this I here, which says that the Magnus force is perpendicular to the relative velocity between the normal and the superfluid velocity. We can simplify it a little bit. We are doing a toy model, so why not to simplify it? In general, alpha and alpha prime are small parameters. Okay, this is something that you can measure in the laboratory. Okay, so since the normal component of the flow, you have the no-slip boundary condition, the vortex ring is going to be all the time, in principle, close to your particle. You can drop the contributions here associated to Vn, just put 0 here where you have Vn, because the normal velocity is really small, okay, downstream, near the particle surface. Okay, but Vs, and here, since they are multiplied by small numbers, you can replace Vs by the external background superfluid velocity, which is V. Okay, but of course you don't replace this Vs here, okay, the leading term, by anything. This is just the superfluid velocity at the vortex positions. So you get a much simpler expression to work with. We could work with this one, but this is even more comfortable to work with. Okay, okay, so we are ready to write down a dynamical system for this problem. This is a standard fluid dynamics in 2 dimension. You can introduce a complex potential, W, okay, which has to do with the complex potential generated by the positive vortex, the negative vortex, and the particle. Since the particle deforms the flow, the superfluid flow, you have this complete complex potential, okay? But of course, you have to remove singularities when you want to compute the velocity at the vortex positions. So the velocity, the superfluid velocity at the vortex positions is given as a derivative of W hat, okay, plus or minus, depending if you are considering the positive or the negative vortex, okay? And here you have hat means that you have just removed the singularity associated to the vortices, okay? Here we have explicit expressions for W plus and W minus, okay? These are just the contributions associated to the vortices and their images inside the sphere, okay? Omega P, WP here is the field produced by the particle. I mean, is when you insert the particle in the flow, you have a deformation of the flow, which is given by this contribution. Okay, so now we can assemble everything and write down a dynamical system for the vortex, the dipole, and the particle. So Z plus dot, Z minus dot, ZP dot, and then you have here the equation for the force acting on the particle, which is a combination of the drag force plus a contribution which is given by the Blasius theorem. This is the pressure contribution associated to the superflow around your disc-shaped particle. Okay, here we have the contributions that come from the Schwarz description. Okay, and this is like a tautological definition. U is the velocity of the particle, which is just ZP dot. So we have a dynamical system, first order system of the differential equations. Yes. Sorry? Yeah, good question. I commented that on the paper. M to us is an effective thing, so it's basically M over 2 or something like that. Yeah, yeah, or 3/2 of M. You have an added mass contribution. Right, right. Thank you for this one. I'm considering this, but we are going to see that sometimes the vortex, the pole can go away, can detach. One. Right, but you have 2. So this is not going to happen for this configuration. If you change the signs here, then you're going to have this. They are going to meet here. Okay, but then I consider this case is not stable. They are going to annihilate, or I don't know what is going to happen, but it's an unstable thing. Right. I'm considering this mirror symmetric situation, which is the analogous of the actual symmetry in 3D. Yeah, I'm going to show that from numerical simulations. This is stable. This vortex here, it will go around to in an orbit, closed orbit, and this one also. Further work. That's something that we should see. How stable is this? If you replace it a little bit, I guess that they're going to be stable, but it's a matter of discussion, in fact. Right, right. I checked some stability. If you change the distance a little bit, if you change the distance between vortices, it is stable against these perturbations. But I didn't consider the situation where you go a little bit off of the symmetry. Mirror symmetry, but it's an issue that we should take care of. Yeah. Around the boundary? No, I'm considering that from this WP here. The WP, the WP takes into account the Thomson theorem. So I have an exact expression for the flow, superflow around the right, right, right. Yeah, I was afraid of that. I was afraid of that. I was afraid of that, that maybe the particle could go in. But then I ran some simulations with some parameters, and things were okay. Right. Sure. Where you have this collapse. This is something that I would like to understand also. Maybe the Gross-Pitayevsky approach would be interesting, because then you can have like interaction. Yeah. No, no, no. No. No, no. It will not stop. It will not stop. The vortex ring will enlarge a little bit just because of the divergence produced by the vortex ring image. Right, right, right. Yes. Okay, so you have this dynamical system. You have lots of parameters here. You have R, you have V, you have the positions. You have a flux. This is the circulation. I didn't quantize the circulation so far. The phi is an arbitrary value for the circulation. So it's interesting to put the dynamical system into a dimensionless form. So we just rescale the velocity and time and position variables using the natural units that you have, physical units in the problem, the velocity v, the external velocity v, the radius of the particle, okay, and so on. And you can also introduce some dimensionless constants parameters here, A, B, and C, which are associated with the parameters that appear in the dynamical system. C is the drag coefficient, rho is the viscosity, this is the density of your, there is an S subscript here, I missed that. Phi is the circulation, so phi is a product of velocity times distance, and here C is a dimensionless parameter. So you can put all the dynamical system into a dimensionless form, and this is what you get. This is much clean, okay? It's much cleaner. You get rid of all of the dimensions. Now you're working with dimensionless way. All right. So the Blasius integral can be done exactly, and of course this is analytical. You have analytical functions you can integrate perfectly, exactly. And you have 3 terms, but 2 of them cancel just because of the symmetry. And here again, the symmetry can be an issue. If you don't have symmetry, you have to consider all of these guys together. But then you can forget about these 2 first terms here and consider just this, the third one. Okay. All right. So the problem is that, okay, we have a mathematical model, we have the dynamical system, but the phase space to explore is very huge because you have, first of all, you have to know where to locate the vortex dipole. What are the initial positions? What is the initial velocity of the particle? And what are the parameters that you are going to use in your model, alpha, alpha prime, A and B and C? Okay, so you have like 8 parameters to define, to try to explore these numerically. So the idea is to run simulations and to see for each one of these phase space points, you have distinct behaviors of your system. Okay, the first thing to do is that we can really fix interesting values or explore interesting values for A, B, and C, getting some inspiration from the real world. So rho, the density in 2 dimensions, can be written like the density, the 3-dimensional density of the superfluid times the particle radius. Okay, the mass of your particle is rho p, the density of particles of the deuterium, for instance, multiplied by the cube, radius cubed, and so on. This is the drag coefficient that you have in Stokes' law. Okay, the usual one. And phi, you can replace phi by the circulation quantum, k, kappa. All right. And this way, you get expressions for A, B, and C. A, so it depends on some physical quantities. Okay, you can estimate them. So just go for some experimental work and take data from these works to estimate the values of A, B, and C. So you see that these are small numbers, 0.3, 0.5, and C is equal to 2. Which is something amazing because you were working here with numbers with very different orders of magnitude. By the end, you get some nice numbers, not that big or small, okay? But it remains still, and alpha prime, we're just going to cheat from the 3-dimensional values. Alpha is 0.3, alpha prime is 0.01. Okay, so I took in all the simulations alpha prime equal to 0. And alpha equal to 0.2. I don't remember why 0.2, but I think it was, okay, it's around this. There's nothing very important with I could have taken a 0.3. But alpha for us is 0.2 and alpha prime is 0 just because it's so small value. It does not going to change anything. But we have also to realize what is, to figure out what are the initial conditions, the positions for the vortex, in the vortex dipole and initial velocity. So we're going to take the vortex dipole as close as possible from the particle, since we want to explore these bound states. Okay, where this is the choice for the initial conditions, and we're going to take the particle at rest initially. So this is the picture. Okay, more or less that's what we have. The vortex dipole is really close. Okay, the x horizontal position of them is just the radius, but they're just a little bit displaced vertically. Okay, and half of the radius. Okay, and the particles is initially at rest, and then you run your simulations. Okay, well, you have 3 possible flow regimes here. Okay, you can have, this is what we are going to get. You can have the particle moves along the normal flow direction. Okay, let's call this a forward moving VRP states. VRP stands for vortex ring particle states. The particle and the vortex ring can move backwards, okay, or they can get decoupled. Okay, let's call these a vortex particle decoupled states. And in this case, the vortex ring will enlarge because you have a Magnus contribution to the velocity, which is perpendicular to the translation, horizontal translation velocity. So we have these 3 states. We want to see when you get each one of these 4 different different parameters in your phase space. So this is some of the chart flow regimes that you get. We're changing here parameter A from 0 to 0.2 and C from 0 to 1. Okay, for different values of B. B is the parameter which is in front of, it's basically the density, dimensionless density of the fluid. A is related to the drag, okay, and the drag coefficient, Stokes' law, and C is related to the circulation. Basically, that's it, what you get. Okay, and then, so green regions here mean that you have forward-moving VRP states. They move along with the normal flow. The blue ones means that you have backwards. So it's interesting that you can have it here inserted in these charts. You can have things the particle can move opposite to the normal flow. And the red regions are just the regions where you don't have any coupling. Okay. It's an interesting observation here is that it seems that you have lines which bound these regions. The backward moving region it seems to be bounded by straight lines, and this is something that you can understand if you look at the definition of the A and C parameters. They depend on the velocity and the radius of the particle. Here you have the definitions of them. So A, it's basically inversely proportional to the product of V and R, okay, and C is also inversely proportional to V and R, but here I have the circulation quantum kappa. So the ratio between A and C, okay, doesn't depend on V and R. So if you do an experiment, okay, and if you change the heat flux, for instance, you're going to change V, but the ratio between A and C is not going to change, it's the same one. And the same thing if you change the radius of your particles, okay, you have some spread in radius in the experiments, so the ratio between A and C is fixed also. A over C constant is depend on physical parameters. Okay, it's associated. This is associated to these lines, which you call physical lines, just because of the fact that when you do an experiment, you're not exploring all the phase diagram or the chart, but you are running. You're going along one of these dashed lines. Okay, if you change the heat flux, this means that you're going to walk along these dashed lines. Okay, so this is why they are called physical lines. But here, then you can also estimate the velocity of the particle. It depends on the geometrical characteristics, geometrical features of your orbit, stable orbits. Okay, but this is a little puzzling because we know that in experiments you have sometimes you have particles that go with the normal flow. Okay, so this is what you would have. Okay, and sometimes you have particles that are just detached. So this curve here, this dashed line here, okay, this is given by this solid black line here. So velocity 1 means that you are in this region. When you cross this region, you go to the situation where you have the vortex ring is attached to the particle, and then the velocity drops. But you see that along a vortex line, the velocity doesn't change too much. So this means that the velocity should be peaked, like you see in the experiments. Okay, it peaked here. There is some small variation of the velocity around this peak, but then as you move to this region, if R gets smaller, then you decouple the vortex ring to the particle. Okay, and you get unit velocity. So that then the particle you have the peaked Vn distribution, and here you have the peak at Vn over some. Vn multiplied by some factor, which is not always like 1/2. It depends on the value of your ratio between A and C. But since we have particles that move backwards, how to make this thing compatible with experiments? The point is that, so this is a conjecture, is that if you change the value of the quantum here, circulation quantum, so consider that you have like topologically excited vortex rings. Okay, you can have 2 or 3 quanta of circulation in a vortex ring. Then you change the steepness of these dashed lines. Okay, so this line here is associated to vortex rings which have a larger circulation. Okay, so this is, let's say, this is for the single quantum, and this is for, I guess, 4 quanta, 4 circulation quanta. And in this way, you can enter into the region of backward moving states. Okay, so the idea is that backward moving states, okay, would be associated to the attachment of vortex rings, which have higher topological numbers. That's the claim from this model. So you see that here you also have peaked values at negative values of the velocity, which are not so large like the ones that when you go along with the normal flow. Okay, right. So once we have these results, we can explore what are the different contributions for the velocity of, let's say, the positive vortex here, Z plus dot. You have basically 4 contributions. The first one associated to image vortex. of your positive vortex here. You have another one which is associated to the partner, to the vortex dipole partner, and the image of the vortex dipole partner. Okay, and you have a contribution that comes from the vortex, from the background, for the superflow background. And finally, you have the contribution that comes from the Schwarz description, I4. So we can compare the background superflow contribution with all the others and see how this competition goes along. So here you have the imaginary parts of that contributions. I am considering the contributions of the superflow background as these dashed lines. This is the imaginary part of I3. And I'm summing all the others contribution into a single contribution, imaginary of I1, I2, and I4. Okay, the solid line here. Okay, so you see that this is the trajectory. This is a sample of the trajectory of the vortex dipole. So when you go from A to C, okay, the background loses the battle against the other contributions from A to C. And this is clear from here, from the picture. So from A to C, the vortex, the background superflow tends to push the vortex to the left, but it's moving to the right. This is the reference frame of the particle. Okay, so from A to C, you have this dominance of the images and of the vortices as a contribution to the velocity. But then from C to A, okay, you have the opposite. And here is when the background wins this competition. 3 minutes, okay. Here, this is for the vertical velocity. So here you have the vertical returning points A and C. And here you have the same considerations for the horizontal velocity. Okay, so from B to D, a dashed line dominates. Okay, this means that the background is the strongest contribution from B to D. So we go to the left, the superflow pushes the vortex back. Okay, and then it loses the battle again. And the nice thing is that you have a stable orbit in this process. Okay. Of course, we should see here that there's a close contact. They are very near. This is kind of dangerous. Maybe there can be some reconnection. I don't know. Maybe the Gross-Pitagoric approach can be of interest here to approach this problem. Okay. It's interesting also to see what happens if the Magnus, the mutual friction coefficients for the Magnus force is changed. So I fixed here the drag coefficient, alpha prime is 0 all the time, but the variable alpha is taken here. We took 3 values for alpha, 0. So you have a small orbit on the top of your particle. This is the particle, this solid black line here. This is a zoom to see how the trajectory looks like. Okay, as you make alpha larger, okay, for instance, you see that the orbit is displaced to the left and the orbit gets enlarged up to the point where then you can not sustain this orbit anymore, and then you have a decoupled state. The vortex goes away. Okay, so and it's interesting that if alpha is small enough, okay, the particle will be dragged by the normal flow. But if alpha is different from is larger than some threshold, the particle will be dragged backwards. And if alpha is even larger, then you have a decoupled thing, and the particle, the decoupled state, and then the particle will follow the normal flow. So the Magnus force has a very important role here. It has been inside some window of parameters, such that you can have backward motion. Backward motion is associated to the Magnus force. Okay. So conclusions and open problems is that the toy modeling, okay, is able to recover things that we already know, like the backward or forward moving VRP states with scaled velocities. Okay. The physical lines, they imply that the velocity distributions have peaks. This is observed. Okay. And also, if you get back to the chart, the diagrams, you see that if A is very small, you just have red regions here, which means that you don't have coupled states. So if viscous damping is small enough, okay, if viscous damping is small enough, you don't have bound states, okay? And this is related to something that was already observed by Kibotidis, Sergiv, and Barengi in the Physical Fluids 2008. They noticed that if dissipation is small enough, you don't have attachment between the particles and the vortex filaments. Okay, yeah, it's not your wife, right? It's just me. Yeah, yeah. Okay. Just concluding here. So VRP states and things that we okay. So this is what we already know, and it's compatible with the model. And this is what something that maybe the model is suggesting us to take a careful look at. As VR space states are not stable if Magnus mutual friction are too large or too small, and we can change the friction coefficients, change the temperature, for instance. The topological excited vortex rings, they may play a role in the existence of backward moving VRP states. This is another claim from this. This is also interesting. So since you have these oscillations of the vortex ring which are attached to the particles, you have translation, okay, for this VRP state, but then you have small oscillations. And so they are associated to pressure fluctuations, pressure oscillations, okay? If you have thousands of these particles, for instance, in the Shrek experiment, you have a very large vessel to study. It may be that the superposition of this acoustic peak can be detectable. I don't know, but we can estimate that. Okay. So further work that would be very nice. It's okay, of course, to extend all of this to 3D modeling along the same lines, and this is very feasible. But in 3D, things are a bit boring because then you have to work with elliptic functions. The vortex ring images are more complicated. Okay. So you have not the beauty of 2D flow, of course, but it's something that's feasible. It would be very interesting to work out some gross Pitaevsky modeling of these states, of these bound states. Okay, and I think that this is a very important thing to study. Is some scattering modeling of the particle vortex interaction. I would like to have some cross sections for the formation of vortex rings, for instance. In the collisions. This would be a very important ingredient in getting information from the PTV experiments, okay, that people are doing now at this moment. Thank you very much for your patience.